This is lesson 12.5, independent and dependent events. Today we're going to learn about conditional probability, and this is the last lesson of unit 12 on probability. So first we'll talk about the difference between independent and dependent events. Two events are independent if the occurrence of one event does not affect the occurrence of the other. So does not. So it doesn't depend on anything else. I like to think of it as like the sun rising. The sun rising, besides gravity and stuff like that, the sun rising does not depend on anything else. It's always, it's always going to rise. But what you eat for breakfast might depend on what's in the house or how hungry you are. So that would be like dependent events. So the occurrence of one event does affect the occurrence of another. So maybe you had a really big late night snack and you're not that hungry for breakfast, something like that. That would be dependent. So here it says a jar contains red and blue marbles. You randomly choose a marble from the jar and you do not replace it. Then you randomly choose another marble. Tell whether the events are independent or dependent. So the first marble you choose is red, the second marble you choose is blue. Well, after you choose a marble the first time, the second time you have one less marble in the bag. So that means that if you have one less marble to choose from, event B is dependent on what you select in event A. And maybe you selected a blue marble first, and that means you would even have less blue marble. So this would be dependent. These would be two dependent events, because the outcome of the first one affects the outcome of the second one. And so with conditional probability, you're looking at the probability of an event B occurring given that another event has already occurred. So it's kind of like, what's the probability that the second marble you choose is blue given that the first marble you chose was red? So for conditional probability of B given A, the way we notate this is the probability of B, and then the symbol for given that is this vertical line. It's kind of like if you see the slash bar on your keyboard and that line above it, if you press shift in that line, that's what we're talking about here. So the probability of B given that A already occurred. And then A and B are independent. So if A and B, if the two events are independent, they don't affect each other, that means that whatever you get for the probability of B is going to be the same thing as the probability of B given A, because if they're independent, then A doesn't even matter. So the probability of B given A is just the probability of B, because A doesn't affect B. And then for A given B, it's just the opposite. So probability of A given B, and then A and B are independent only if the probability of A is the same thing as the probability of A given B. So I like to think about it as like the probability that the students are in the band. So you would do the number of students in the band over the number of students in the whole school. But what if we're only talking about the number of students, or what if we're talking about the probability that they're in the band given that they're in 8th grade? Well, then you're not just taking the probability that they're in the band, you're taking the probability that they're in the band and 8th graders over only the probability that they're 8th graders, or the total number of 8th graders. So this would be the probability that they're in the band given that they're in 8th grade. So you're only selecting out of those 8th graders, how many of those 8th graders are in band. And then that's different from the probability of being in band and an 8th grader, because that probability is looking at the total. So this is like the probability of band given 8th grade, and then the probability of band, this is supposed to be an 8, and 8th grade is even something different. Okay, so got a couple of different things going on here, but we're also going to talk about a rule on the next page for this, so this little box here. So for independent events, if the two events are independent, the probability that both events occur is just the product of the probabilities of the events. This is like the multiplication rule for probability. So the probability of A and B is the probability of A times the probability of B. Now remember from lesson 12.4, the probability of A or B equals the probability of A you add. So when you see or means add the probability of A plus the probability of B, but then you have to subtract the overlap of A and B. So this is how you would find the probability of A and B, is to multiply the two events together. So I think you are aware of that rule before. But if they're dependent, then you would do the probability of A and then times the probability of B, given that A already happened. So that's, if they're dependent, then this will be different from just the probability of B happening on its own. So let's see. So the next two examples are using the difference between independent and dependent events. So as part of a board game, you need to spin the spinner at the right, which is divided into equal parts. Find the probability that you get 25 on your first spin and 50 on the second spin. So the spins for the first spin and the second spin are independent of each other. The second spin isn't going to matter what you spin on your first spin. So we're just going to multiply the two probabilities together. So for 25, there's two 25s on here. So that would be 2 out of 8. And then for the 50s, we're going to multiply the probability that we get a 50. There's just 1 50. So that would be 1 over 8. Okay, so if we simplify, this would be 1 over 4. And this would be 1 over 32. And then for dependent events, it says, I don't know what happened to my space down here. Okay, here we go. Let's see, you've got 36 green grapes and 14 purple grapes. You randomly choose a grape, eat it. So that means you do not replace it. Okay, so the do not replace part, or eating something, not putting it back, that's going to mean that the two events are going to be dependent, because what you pick the second time, if you're not replacing it, that's going to affect what you pick the second time, or the number of outcomes that you have left. So, and then you randomly choose another group. So find the probability that the first grape is green and the second grape is also green. So for the first grape being green, you've got 36 green grapes out of 50 total. But then you have to multiply by the probability that the second grape is green. Well, you're assuming you already ate a green grape, so that means you only have 35 left. And if you already ate a green grape, then there's only 49 total grapes left. So if you multiply those two probabilities together, you get 1,260 over that number. I didn't do that in my head. I already calculated it before this. And then that would be 0.514. If we did it to decimal, it'd be 51.4%. Okay. And then that's the exact same thing. So there's another way we can rearrange the formula for conditional probability. So say we took the formula previously on this slide and we wanted to solve for the probability of B given A. We would divide both sides by the probability of A and have the probability of A and B divided by the probability of A. So what am I talking about? So the other way to rearrange this formula is, if you wanted to rewrite it for the probability of B given A, you would put the probability of A and B over just the probability of A. So I was kind of alluding to that with the band and 8th grade example. So that's another way you can think about this formula. I'm pretty sure this is one of the formulas that'll be on your air test on the formula sheet. Okay, so there's a couple examples with tables where the formula is nice to have for reference, but you don't really need it. I'll show you how to do it without the formula. So you just use logic. So say we've got this table shows the number of tropical cyclones. So you've got tropical depression, tropical storm, hurricane. I'm not sure what the difference between depression, storm, and hurricane are, but maybe you could ask your science teacher. And then use the table to estimate the probability that a future tropical cyclone in the northern hemisphere is a hurricane. So in the northern hemisphere is a hurricane. So out of the ones that are northern hemisphere, so what we have to do is add up all of these and add up all of these and add up all the rows and columns. Okay, so let's go ahead and take a minute to do that. So 199 and 18 make 217, 398 and 200 make 598, and then 545 and 215 make 760. And if you add these two, just to cut to the chase, you get 1142, and then you get 433. And the good rule of thumb is to add up these, and you should get the same number for the total, which is 1575. So when you find the probability that a future tropical cyclone in the northern hemisphere is a hurricane, so you're looking out of the ones that are in the northern hemisphere, which is 1,142, there are 545 that are hurricanes. This is part A. So if you divide those two together, you get about 0.477. Right, so that answers that question. And then the probability that a hurricane is in the northern hemisphere. So out of all of the hurricanes, 760, what's the probability that it's in the northern hemisphere? 545. And that gives us about 0.717. So you've got to be careful because A and B, they sound like they're the same thing, but they're not. The given that here is given that they are in the northern hemisphere, but the given that here is given that it's a hurricane rather than a tropical storm or a depression. So you have to be careful that you're reading the question correctly, because if you don't, then you'll find the wrong answer. Okay, and I'm actually going to put this into 2 videos. So this is part 1. So you can go ahead and find part 2 to the video and watch that.